Okay, in the first couple of chapters, we dealt with differential calculus, where we were taking the derivative, looking at the slope of your tangent line. We're now going to shift gears and more or less look at the reverse process. There were applications to derivatives. There's applications to the reverse process. The reverse process is more or less integral calculus. Uh, the reverse process of taking your derivative is often referred to as your integral. We know from what we talked about in our first two packets that we had the derivative, which was the slope of your tangent line. We also had the area underneath your curve, which was referred to as your integral. Here we have what's referred to as a definite integral because we have your upper and lower limits. So here, in this particular problem, we're looking for your area between 2 and 6 on your x-axis of this function. And that's displayed over here in blue. Now, this means find the area between 2 and 6 underneath that curve, between that curve and the x-axis. You will learn out how to get the exact answer later, but that's here, and here's your decimal approximation. We also have what's referred to as an indefinite integral. An indefinite integral is like this one down here, where there is no upper and lower limits. Basically, if you start with your function and take your derivative, you get your derivative. If you take your derivative, apply your antiderivative, which is your integration, you get back to your original function, or vice versa. Now, when you're dealing with derivatives, there were applications. Also with integrals, there's applications to motion, velocity, population growth, volume, surface area, and center of gravity. These are all applications of integration, which is the reverse process of differentiation. Sometimes integration is referred to as the antiderivative. Now, quickly go ahead and take your derivative of all four of these functions. You'll notice for the first one, you get a 3x squared. For your second one, you get a 3x squared. For your third one, you get a 3x squared. For your fourth one, you get a 3x squared. Those are your derivatives of your original functions. So if we wanted to go ahead and find your antiderivative of your 3x squared, well, your antiderivative of 3x squared, you go integral 3x squared dx. The dx, the x is telling you what variable you're integrating, so we're integrating x here. So you know that this is the derivative of some function. You're trying to find that original function. That's what antiderivative means. Well, 3x squared is the derivative of an x cubed. But as you'll notice up here, we had different x cubed functions that all gave you the same derivative. So really, it's a 3 or an x cubed plus some constant that we don't know, which we call c. C is referred to as your constant of integration. Since there are multiple functions that give you this derivative. In general, we would say when we integrate, we're going to get a function, and then we got to go plus c, where c is your constant of integration. An indefinite integral is what we have right here because there's no upper and lower limits. So in general, whenever you're dealing with an upper and lower limit, you're going to go back and get your original function plus c, which is your constant of integration. So let's go ahead and think backwards on these. You're used to taking your derivative. We're now working backwards. Your 3 is your derivative, and so what would your original function have to be to get a derivative of being 3? Well, you would say a 3x. But remember, since it's an indefinite, you got to go plus c. If you forget plus c, once you get to your test, that's 1 point per problem. If you have 10 or 15 questions like this and you forget plus c in all of them, that's a lot of points you just missed. So now you got to think, okay, 2x. 2x is the derivative of what? Well, that's an x squared, but then you got to remember plus c. Over here, x to the fourth. Well, you know you got to increase your exponent by 1 because you know with derivatives you decrease your exponent by 1. Derivative or integration is the reverse process, so you got to increase your exponent by 1. Gives you an exponent of 5. You then got to think, okay, what would I have to have in front to undo that power of 5 when I put it down for taking the derivatives? If I took my derivative of the x to the fifth, that would put a 5 down in front. I don't have a 5 hanging out in front here, so you'd have to have a 1/5 in front to undo that, still with your plus c. Once again, the plus c is referred to as your integration or constant of integration. Capital F, what we were finding here is your antiderivative. Variable of integration is whatever is after the d, in like dx or dt. If you had a dt, you'd be integrating with respect to t. And then you have your integrand. So we want to think, okay, the derivative of what is cosine? Well, you should remember that that is just sine. But then you got to remember your plus c. Now you got to think, okay, the derivative of what is sine? Well, you would know that that would be a negative cosine and a 5x. But if you were taking the derivative of this, the chain rule would said you'd have to multiply it by the derivative of a 5, which is, or inside, which is a 5. You don't have a 5 hanging out in front, so you'd have to somehow undo that. So that's why we have a negative 1/5. The negative coming from here, the 1/5 is there to undo the derivative of the inside. And then you'd have to have a plus c. So if we generalize some of this and we're looking at integrating x to the k, remember you got to increase your exponent by 1. So your exponent would be a k plus 1. But then if you're doing your derivative, that would put a k plus 1 in front. You don't want a k plus 1 in front. You just have a 1. So you got to think, okay, what do I have to have in front to undo that? That's a 1 over a k plus 1. Then you got to remember, oh yeah, it's plus c. Now, they do have an exception here that it can't be equal to negative 1. And that's because when you integrate 1 over x, and that's what x to the negative 1 is 1 over x, it really gives you natural log. We'll be discussing that, though, in the next chapter. So go ahead, if you remember your definitions or your derivatives of your 6 trig functions, you should be able to do this page. So go ahead and try to do that. So here we have the derivative of something is cosine, which you know is sine. But then you got to undo the derivative of the inside, which is a k, so that's why we have a 1 over k hanging out in front. Derivative of something is sine. That's a negative cosine, but once again, you got to undo that chain rule of the derivative of the inside, which is k, so we got to have a 1 over k in front. Derivative of what is a secant squared? Well, that is tangent, so it's 1 over k times the tangent of kx plus c. Derivative of what is secant squared? Well, you should remember that that deals with a cotangent, but the derivative of cotangent gives us a negative, so that's why we've got to have a negative in front to offset that. Got to have the 1 over k to offset the chain rule of the derivative of the inside. Over here, you got to think, okay, the derivative of what's a secant tangent, and that is your secant, so it's your antiderivative is secant of your kx, because that's what's after your secant and tangent. And you get a 1 over k and a c. And then similarly over here.